Next generation RF communication systems need to reduce both footprint and power, while at the same time increasing the hardware flexibility to address a wide range of use cases or radio variants. Xilinx is integrating direct RF sampling converters into its MPSoC devices to create a new all-programmable RFSoC family to address these challenges. In a moment, we will look at the performance of a recent 16nm FinFet test device. But first, let's review some of the benefits of direct RF sampling technology. Today's radios are typically implemented using analog signal processing techniques, similar to what's shown here. As we can see, the frequency shifting and selection is carried out in the analog domain, and the data converters operate at or near baseband. Some programmability can be added to these analog signal processing blocks. However, there are limits to what can be achieved in terms of flexibility and performance. But when we move the data converters closer to the antenna and carry out more of the frequency shifting and selection in the digital domain, we have a robust, highly flexible platform for radio implementation. With direct RF sampling converters, this is now possible, and we can take advantage of advanced CMOS technology to implement very power-efficient programmable RF signal processing. Let's take a look at the converter performance which can be achieved in advanced 16nm FinFET technology using digitally assisted techniques. The board you're seeing here contains a 16nm FinFET test chip with both 4 giga-sample per second RF sampling ADC and a 6 giga-sample per second RF DAC. The converters were evaluated across process, temperature, and power supply variation, and the built-in calibration and digitally assisted techniques delivered industry-beating levels of performance. For example, here we're looking at the output of an RF DAC on an FSW spectrum analyzer from Rohde & Schwarz. Excellent performance was observed for the RF DAC, which here is generating two tones centered at approximately 1.9 GHz and separated by 20 MHz. The third order intermodulation distortion, or IM3, at minus 65 dBc illustrates very high linearity of the DAC. To test the ADC, a high-quality signal source, such as the SMW200A, also from Rohde & Schwarz, was used to synthesize both carrier wave and modulated waveforms. Additional analog filtering provided the signal purity required to evaluate the RF ADC. Data captured from the ADC was analyzed using FFTs implemented with LabVIEW software from National Instruments. Here we can see the FFT of a 1.9 GHz input tone sampled at 4 gigasamples per second. The second and third order distortion components are aliased in band to the first Nyquist zone, as indicated by the red colored markers on your screen. Other distortion components shown are interleaving artifacts, which are greatly suppressed by the built-in digital calibration. For more details regarding the performance of the RF sampling ADC and DAC shown here, please refer to two papers published at the Gigahertz Converter session at ISCC in February 2017. The integration of direct RF sampling converters with our 16nm MPSoC devices greatly increases the flexibility of the RF platform, while at the same time reducing footprint and power. Please visit Xilinx.com to understand more about the unique benefits of the all-programmable RF SoC.